All right, so if we take this piece of paper here, and you're going to start by folding it in half this way. Just fold it in half and crease it. Ugh. Okay. And then, sorry it jumps a little bit, but in order for me to record, it has to jump a little bit. So when we open it, then you open it back up and do what I think is called the shutter fold. I don't really know the fancy names, but basically fold this into the middle, both sides into the middle. Then you are going to cut. Please use your brain and don't cut this thing completely in half. When you open it up, you're going to cut along these lines to the screws. So you're only going to cut to right here because you're making little doors. Just to right there, that first little crease. Twice on this side. And then twice on this side. Make sure you cut on the correct lines. It should make sense. So it then looks like this. Okay. So we're going to call this PPD RAT2EY or RAT2EY. It took me a long time. I was somebody that called it RAT2EY, and I was like, I don't really see how that's like where she's getting that from or how that pronunciation, but do y'all see why it might be pronounced that way? Because it's RAT2EY. Get it? It made sense when somebody pointed that out to me. I was like, oh, I get it. I thought they were like trying to say ratatouille and couldn't say it right or something. I don't know. But two T's, it's more like than ratty, but I don't know ratty, so we'll just call it ratty. As long as you know what it is, it doesn't really matter. As long as you know that there's two T's, we are good. Okay, so PPD RAT2EY is what we'll call it. So on here under PPD, I want you to write RAT, almost like T squared, EY. So RAT2EY, but there's two T's in RAT2EY. So let's talk about this PPD part of this first. So once we have that, let's see if I can zoom in. I figured this would make more sense than me trying to do it on the board up there. We'll see how coordinated I am with this. Just open this little thingy up. Okay. So the first thing we look at is when we're trying to graph, because we're going to be graphing rationals. Maybe I should tell you that. That's why we're even doing it. So graphing rationals is going to be different than graphing polynomials. They have different properties and different rules. So the first thing we want to look at is, does it have a parent? Is there a parent function that we know that we can use? I'll read that okay. Oh my goodness. There we go. Does it have a parent? That's what it says to me. So there's two parent functions. We really only talked about one, and that was the f of x equals 1 over x. Remember, a rational function has a function in the denominator. And do you remember what that looked like? Anybody tell me? What does the 1 over x function look like? Has the two asymptotes? Yeah, and it's kind of like the two C's, yeah. All right, y'all got it. Good little hand motions there. This one. And I'm sorry, I know my hand's in the way half the time here. My body's in the way when I'm on the board, and then my hand's in the way here. So then the other parent function that there is for rationals is f of x equals 1 over x squared. So if I have 1 over x squared, tell me about the y values that I would end up with? Are they bigger or they be smaller? Once I substitute in x, if I substitute in 2, this is 1/2. If I substitute in 2, what is this? 1/4. Okay, so the values would be smaller, but what happens on this side of the x-axis? I'm sorry, this side of the y-axis. Am I ever going to have any negative answers? Nope. Okay, so it reflects, so it looks like this. Okay, so basically all of your x's are positive. And the graphs don't look identical with just that reflected because, like we just said, the y values are smaller, so it has the same shape. But so if it does, we just do transformations. But unfortunately, most of them won't have parents. They're like orphaned functions. PD, so the P is for parent. PD is for point discontinuity. PD is for point discontinuity. So how do we get point discontinuity? Do you remember? Okay, we factor and then we cancel anything out, right? So that means that we'd have to have a factor or factors containing x that is common to the numerator and the denominator. Everybody okay with that? Is the PPD. The R stands for roots. What's another word for roots? Zeros. Do you know that sometimes zeros has an E in it down here? Do you know what the difference is? It's whether it's a noun or a verb. So this is a noun, like zeros, it's a thing, right? But if something zeroes out, like the function is going to zero out, right? Because they cancel out. So when it zeroes out, and that's like a verb part of that, that's what's actually happening to it, then there's an E on it. I had to Google it because I get confused because I know sometimes there's an E in it. Rarely will we write the E, but sometimes it's there. All right, now we're going to open that up. Okay, so roots. Good. X-intercepts are the zeros of the numerator. Okay. So we know that, right? It's like finding your zero. It's only the zeros of the numerator. Those are your x-intercepts. Those are your roots. But we call them roots on here just the radii. I guess having them be a zany. That is always found after reducing. That's important. If you find it before you reduce, it's zero when you don't. Here is for in just a minute. Get ready for asymptotes. Open this little going to be the denominator. And these are lines, line or lines, determined by the zeros of the denominator. And then I need to add something. I just realized I left off of here. You find these after reducing. On the denominator does not mean that you have an asymptote. All right. The t squared, am I going too fast or y'all good? Okay. T squared, this stands for 2, which is really 2 things. And they both start with a t. Not just the 2 and the things, but the 2 things that we're using start with a t as well. So when we open this little door, so this says, do any factors of the R, what does R stand for? Roots. Or A, what does that stand for? Asymptotes. So do any factors that give you roots or asymptotes, not the ones that cancel out and give you point discontinuity, but do any of these that you're left over with after reducing have an even exponent? Okay. And remember, we are not graphing polynomials. So it doesn't necessarily give me, doesn't necessarily give me the, like a, I'm trying to get that. Thank you. All right. Can you hand this to Josue when you go sit back down, please? Oh, right, you can get it. Thank you. I just said thank you. Okay. So if we have an even exponent, so you look at how we factored it, right? So that's why it's important that we factor it and then we condense things. So here, the numerator, this factor has an even exponent, right? Not always just 2, but some sort of even exponent. That's still going to give us tangency. Okay. Still gives us tangency, but it gives us tangency either way. So it's going to look like, that means that at this point, it is still a bounce, just like it was for polynomials. So it would bounce like this or bounce like this. Okay, but it's telling you it has tangency. This is important because these are the way we're going to be able to graph these, kind of like we did with polynomials. So if it's in the numerator, it's just like it was for polynomials. If it's in the denominator like this, it gives us togetherness. I know. So we'll talk about tangency and togetherness. Because if I have a 0 in the denominator, tell me what's happening at x equals 3 in this function. Down here, since it's in the denominator. What is x equal 3? What's that giving me? What do your zeros in the denominator give you? Asymptotes, right? Why are we so confused on this? The zeros in the numerator give us zeros. The zeros in the denominator give us what? Asymptotes. So we have an asymptote at x equals 3. Does that make sense to you? So we already know that. But since it's squared, that's where our togetherness comes in. And here's what this means. And we're going to draw 3 tiny little graphs. And then, maybe my x-axis is just a little bit longer here. So then I'm going to have an asymptote. We'll pretend like that's 3. Right? We'll try it 3 times. All right, so this is what we could have. The togetherness, what this means is that you know that they would be either both going to infinity or both going to negative infinity at that point. This is what is not going to happen. So put a circle with a line through it. This is what's going to happen normally with asymptotes. Unless you have an even exponent, then you have togetherness, like these two. Okay, does that make sense to you? So you got to know how it's behaving around the asymptote. Yes, the exponent would have to be on the bottom for give you togetherness. The numerator gives you tangency. The denominator gives you togetherness. Okay, does that make sense? We good? Okay. All right, and we'll show you how to work through this stuff too. So E stands for end behavior. So as x approaches infinity or negative infinity, f of x approaches blank, right? This is what we're looking for. What's happening at the ends? Okay, the asymptote kind of gives us some of the middle behavior. The zeros give us some of the middle behavior, but then the end behavior, what's happening way out there at the infinities, that's important for us to understand as well. Okay, so that's where our horizontal and our slant asymptotes come into play. So if I have a horizontal asymptote, which we will call HA, what happens if your function is top heavy? What's happening with the horizontal asymptotes? None. There's none. If it's top heavy, there's none. There's none, and then there's potential for a what? Slant asymptote. So we'll call that SA. Oh. What's another word for slant asymptote? Oblique. Very good. Okay. So if it's top heavy, there is no horizontal asymptote. That's when it opens the door for a potentially having a slant asymptote. If that happens, then the degree of the numerator has to be what? How much greater? 1. 1 greater, not just greater, but 1 greater in degree than the denominator. So if that's true, then we divide and we do what with the remainder? Ignore it. So yesterday in the video that you watched, I explained what the remainder actually means. Does that make sense to you? How it's the distance from the function from the asymptote itself. Okay, so oblique asymptotes or slant asymptotes only if it's top heavy by 1, right? All right, so back to the horizontal asymptotes then. If it's bottom heavy, what's true about the asymptote? Y equals 0. Good. And if it's tied in degree, then y equals the ratio of the what kind of coefficients? Leading coefficients. And it's important that you understand it's not always the first numbers, it is the leading coefficient. Most of the time they are written correctly and written in order, but not always. So don't always just look for the first number, make sure it's actually the leading coefficient. Okay, yes ma'am. You do because, well, you need to have it factored because you need to make sure that you've actually reduced it all the way first, so you'll always factor it. But then when you actually divide, then you're going to want to use the non-factored version so you can do the division. Does that make sense to you? Okay. All right, so then Y stands for the Y-intercept. How many Y-intercepts do you potentially have? 1. Can't have more than 1. Right? All right, so how do we find the Y-intercept? We substitute 0 in for what? X. And then we solve for Y. Because it is called an intercept, we always write it as what? An ordered pair. Very good. All right, what questions do you have? Nothing yet? Okay. So this just kind of explains, so these are all the things that we've done, right? Like none of this was new information because I didn't teach you how to do any of it. That's just, I'm just telling you what the letters mean in this acronym because we're now going to use this. Keep this handy and grab your other piece of paper. Oh, shoot. What page did this go on? 55, that sounds good. Was yesterday's 54? Okay, so on the back of this you can write page 55. And then when you put this in, you don't necessarily have to glue it. You can put it in. You can put it, just like set it down in your ISN like this, and then put a piece of tape at the top right here and at the bottom. And then same with these graphs. These graphs I tried to format where we could put them in like we've been putting everything else in, but then the graphs were too small, and I just didn't like it that way, so I kind of had to do them this way. So when you tape these in, now on this one, this back is blank. And they won't all be blank from what we're doing this week. So what you could do, so that if you tape it at the top and the bottom here on the side, that's absolutely fine because we don't need the back. But if you put a piece of tape along the side, then you'll be able to see the insides and you'll be able to flip it over on the back like that too. Okay, won't really matter today, but So if that was 55, then this is page 56 when we're done. All right. So let's talk about our PPD radii that we're going to do. So I'm going to write that at the top here. PPD. Now I have stepped you through that stuff over here and what we're looking for. Okay. But it won't always be there, so you want to like have that acronym in your head, kind of like SOHCAHTOA, like you just kind of want to know what it is so that you know you find all the pieces. All right, so we are going to, it says graph each rational function. Let me zoom in a little bit more. And complete the indicated data. Indicate none if the data does not exist. Basically, if the answer is none, you can't just leave it blank. Okay, hopefully we know that much. So we want to always start by factoring. So start with, this is going to be x plus 2 in the numerator. Denominator is going to give me x minus 3 times x plus 2. So, is there anything that I can cancel out? Yes, and the x plus 2. So when I do that, I know that that is going to give me a point discontinuity. It's going to give me a whole. What is the x value of the whole going to be? Negative 2. Okay, and then we're going to have to figure out what the y value is here in just a second. So once I cancel that out, then my reduced function is f of x equals 1 over x minus 3. Then I need to substitute this negative 10 in, negative 2. This is equal to 1 over negative 2 minus 3. So then my y value is negative 1/5. Okay. Everybody okay with that? All right, so since this is my reduced function, what are my roots or my zeros? Where do our zeros come from? The numerator. The zeros come from the numerator. Do you have any? No. Okay. So if the data does not exist, well, technically the data exists. It's called the empty set. Okay? So the data exists. Not having a root is still some data. So the way you write that is literally what an empty set looks like. You have the little brackets and you have nothing in it. Okay? It's called the empty set. We'll put that in parentheses here. This is the empty set. Okay. All right, so then vertical asymptotes. Do we have any? Yes. Is it x equals 3? And remember, this comes after, both of these come after the reducing. The only thing you do before reducing is the domain, and which it didn't even ask us for, but the domain and the wholes. Because if I look at this right here, it might look like I have a root at negative 2, and I don't. It also may look like I have a vertical asymptote at negative 2, and I don't. Okay. So then I look at tangency and togetherness. Do I have a factor that has an even exponent in the numerator or the denominator? No. So my answer is none there. So, in behavior, is this top heavy? No, which means which means that I will not have a slant asymptote. That's the only way I get it, right? So it's not top heavy, which means I am going to have a horizontal asymptote, and it's bottom heavy, so what is it? Y equals 0. Then I need to find the Y-intercept, so I need to find f of 0. F of 0 is 1 over negative 3 then, so it's y equals, oh no, it's not y equals, I'm so sorry. I'm telling y'all, I'm still not fully with it. 0, negative 1/3. Now there's a number line there. I don't even really necessarily need it. If I can graph this without it, then I don't necessarily need it. Okay? But we're going to do it anyway just so you understand how it can actually help you. So to use our number line, we use this, right here. And we put our zeros and our asymptotes on this number line. Well, the only thing we have is a 3. You agree with that? And so I'm going to rewrite this down here so I don't have to keep. So f of x is equal to 1 over x minus 3. And then I substitute stuff in. So something between negative infinity and 3, I can use 0, right? So if I use 0 and I substitute that in, then it's going to just be negative, right? And if I use 4 and I substitute that in, it's going to be positive. So here's what that tells me when I shade this in. This, from negative infinity to 3, the whole thing's negative. From 3 to infinity, it's positive. Okay? So that pretty much tells me exactly what my graph is going to, well, not exactly what my graph is going to look like, but some of the important things. So now I'm going to go and plot these things on my graph. I'm first going to plot this whole, which is at -2, -1/5. So -2, -1/5 is about right here. So I'm going to go ahead and put an open circle there because there's a hole in my graph. I don't have any zeros, so there's nothing going on my x-axis. I do have a vertical asymptote at x equals 3. So I'm going to go to 1, 2, 3, draw in my vertical asymptote. I have a horizontal asymptote at y equals 0. So I draw that in. And then my y-intercept is at 0, -1/3. So I get 0, -1/3 is right about there. So then when I sketch this in, I know that it's coming from negative infinity and it's negative the whole time, plus I'm not crossing asymptote. I know that for sure because we can't asymptotes, but I know that I'm not because it's negative the entire time. So it comes in hugging this asymptote like this. It's going to go through that point right there, and then it's going to get really close to this asymptote and come down here. Now, over here, I pretty much know that the whole thing, and there is no togetherness. So not only do I know that because of my sign chart here, but I also don't have that squared, so it's not going to be down here. It's going to be up here. But I need at least one point to kind of help me with the shape of it. So since this is at 3, we can find f of 4 pretty easily. F of 4 is going to be equal to 1 over 4 minus 3, which is 1. So I can go to 4, 1 and make a point, and that tells me that I can sketch in my graph then like this. And that's basically what that one should look like. Okay. What questions do you have? Good so far? Okay. Let's open this up. Okay, so we're going to start by factoring. So I'm going to factor the numerator. This is going to give me x minus 2 times x plus 1 over x minus 2. Have a hole. Yes. My hole is at 2, and then we'll figure out what the point is. So a reduced function of x equals x plus 1. So when I substitute 2 in there, I get 3. So the hole is at 2, 3. Roots. Do you have any roots or zeros? Yes. What's it going to be? -1, because that's in the numerator, right? Because the whole thing's in the numerator. Vertical asymptotes. Is there anything left in the denominator? No. So this would be none. Any tangency or togetherness? Nope, because there's nothing with the squared. None. All right. In behavior, do I have, well, a horizontal asymptote? No. Technically, this thing is top-heavy. And the interesting thing about slant asymptotes is, I mean, it's top-heavy, and the degree is 1 greater than the denominator. Would you agree with that? It's like over 1. So this is a degree 1 over a degree 0. So when you divide, then, your slant asymptote is this. And this is one of those things that where if you try and discuss this with people, and actually, I feel like every year that we have the same discussion with Ms. Archer and Mr. Ackerman and I, and I feel like this year we came up with a different decision than we did last year, but it's one of those things that if you Google it, like people are still fighting about it in the math community. So technically it's its own slant asymptote, but then when you really look at what is an asymptote, it's something that you're approaching, even though you can cross over it, but you're not approaching it if you are your own asymptote because you're already there. that makes any sense to you. So we're just going to go with none, though, because it can get very confusing, and it's fine that it's none. There's no horizontal, and there's no slant asymptotes. Okay. Y-intercept, I would find f of 0, and that would give me what? 1. So your y-intercept is 0, 1. Okay, so I really, really feel like we don't necessarily need the number line here, but we're going to do it anyway just for the sake of you seeing how this number line works and how it helps us. So we put our zeros on there. The only one we have is -1, right? So then I pick something to the left of -1, like -2. So this is f of x equals x plus 1. Let's say I substitute in -2. If I substitute in -2, I get a negative. If I substitute in 0, I get positive. So to the left of -1, my function is negative the whole time. Highlighters. It's negative, and this is positive, right? So then I go over here and I'm going to graph things. The first thing I'm going to graph is the hole, which is at 2, 3. 2, 1, 2, 3. There's my hole. Then I have a root at -1. So boom, -1. And then I have a y-intercept at 1. Now, is that enough for me to get my picture in there? Yep, because we should know it's going to look like a line. So then you use a straight edge, and don't draw through the hole. That's the whole point, that it's a hole. So it looks something like that. And if you look at this, your graph from -infinity to -1 is negative, just like your sign chart says. And from -1 to infinity, it's positive. If all we cared about is when is it negative and when is it positive, our sign chart would have been good enough and we wouldn't have had to graph it or anything. What questions do you have? Anything? Okay, let's do number 3. So we're going to start by factoring. This is going to give me x plus 4 and x minus 3. And then down here I get x minus 3 and x plus 2. You agree with that? Okay. So then I'm going to cancel these out, which means I have a hole, and the x value for that is 3. And you will not get a hole every single time ever. Just in these 3 examples, you happen to get a hole. And then, so then I get f of x is equal to x plus 4 over x plus 2. Right? In order for me to find the y value for this hole, I have to find f of 3 with my new one. So this is going to be 7 over 5. And can I reduce that? Nope. So it is 7/5. Do we have any roots? What would it be? -4. Do I have any vertical asymptotes? Yes. At x equals -2. And you would never put that in the squiggly brackets because those are equations of lines. Okay. Any tangency or togetherness? No. We'll see some of that tomorrow. All right. Is it top heavy, bottom heavy, or tied in degree? Tied in degree. So do I have a horizontal asymptote or slant? Horizontal, which means there is no slant because you can't have both. And then what is my horizontal asymptote? Y equals 1. Very good. Then my y-intercept is going to be f of 0. And so that's going to be 4 over 2, which means I'm at 0, 2. Okay. What questions do you have? Okay. So let's see what's happening on our number line here. On the number line, I put the asymptotes and I put the zeros. So I'm going to have something at -4 and at -2. Okay. So, and I'm using f of x equals x plus 4 over x plus 2. So if I substitute in like -5, -5 is going to give me negative over negative, which means together that is positive. If I substitute in -3, That's going to give me positive over negative, which is negative overall. If I substitute in 0, I'm going to get positive over positive, which is positive overall. So then what is happening here is that it's positive here, it's negative here, it's positive here. Okay, that tells me what my graph is going to look like. So I'm going to start graphing these things and plotting this on here. I'm going to start with the whole. It's at 3 7/5. So I know I can go to 3 easily. 7/5 is like 5 2/5. So I'm sorry, no, it's not. It's like 1 2/5. That would make more sense. 1 2/5. So it's about right here, and this is a whole. I have a 0 at -4. 1 2 3 4. I have a vertical asymptote at x equals -2. I don't have any tangents here togetherness. I have a horizontal asymptote at y equals 1. So that comes in right here. And then I have a y-intercept at 0, 2. Okay, so here's one reason why I need that sign chart here. Because, yeah, I have a 0, but I don't really know when I'm positive and when I'm negative, right, without looking at this over here. So it's positive from from negative infinity to -4. So here's -4. So my graph is positive all the way from negative infinity to -4, right there. Doesn't get any bigger than 1, but it's positive. And then from -4 to -2, it's negative. So it comes in like this. And then it's positive from -2 to infinity. So it comes down here and looks like this. Now, given the sign chart and the information that we have, since our horizontal asymptote is at 1 and not at 0, I don't know for sure whether or not it actually crosses that horizontal asymptote, because it could go up and down and get closer and closer, but you won't know that at this point. We're just going to assume that it doesn't. Okay? What questions do you have? Okay, there is no assignment today because I need to do a few more examples with you before I actually give you an assignment. So this was just kind of the introduction to the graphing part of that. You can go ahead, oh dang it, and get that put in your ISN. The bell's going to ring any second.